Hello and welcome to today's webinar on key principles of creating a custom map data layer. My name is Wojciech Tomaszewski. I am a technical architect here at RST Software Masters, and this is my colleague.
Hello, my name is Marta Krawczyk. I am a full-stack geospatial developer at RST.
Our team collaborates with Trans.eu, Europe's second largest logistics platform. We are responsible for three development areas, including geospatial data visualization, route search engines and route cause algorithms, as well as an ongoing maintenance of European spatial addresses database.
Today, we'll walk you through some crucial steps involved in delivering a custom map data layer solution to the end users, starting from sourcing and analyzing the necessary data, enhancing it and preparing it to visualizing it as an actual map layer. We'll briefly cover how important it is to establish a solid business design, define data size requirements, where to look for source data, how to design a data parsing process, and finally, presenting your custom layer.
We'll provide an overview of the process, but also demonstrate how we apply these principles in practice when developing our solution, a custom postal codes layer designed specifically for logistics purposes. Because most of the decisions that we have to make are quite universal in terms of geospatial data manipulation, they could provide some useful insights for creating any custom map data layer solution.
As the first step, even prior to searching for source data, it is beneficial to create an initial mockup. Since the end result is essentially what we really care about, it would be ideal to have a detailed mockup as a concrete design representing the business requirements and the level of desired interactivity. Unfortunately, ideals are hard to attain, and oftentimes not the case we end up working with. So then, we can look at the end user's view functionality, which should be the base upon which all design decisions should rely on, as this can significantly influence the overall setup and success of the desired solution.
Yes, so having a basic understanding of what is required to be built, you can start asking yourself some important questions, like how much data is necessary to store in order to create the required view. You have to take into consideration the data that will be needed for eventual updates and how often those updates would have to occur. Consider also potential data that may be necessary for future use by business decision makers, as business requirements tend to change quite often, sometimes even during the development process. So you have to try to be always one step ahead and allow some flexibility in the data model. Leave room for potential adjustments, including the possibility of modifying the data sources even if needed.
Data that is required to create a view is often substantial. However, the end data, just for presentation purposes, can be limited. So ask yourself another question. How much data is necessary just for presentation? Keep in mind here that oftentimes both static and dynamic data have to be considered. And thus, you need to take into account how the zoom level impacts the data. Will it have to be aggregated and simplified? You could run into data that gets progressively more granular and detailed with higher zoom levels, or you could encounter a more common situation where the zoom level and precision of given data will matter only to some extent and can be recycled in several cases.
Lastly, should the data cover most of the map, or would it be sufficient to have it cover only a portion of it? Because covering whole regions of a map, even with basic information, could exponentially increase the amount of data required to transfer. This is highly specific to your business logic, and only after knowing the requirements can be answered whether or not some of this crucial information can be omitted for optimization purposes. After answering those questions and doing a preliminary analysis, you can typically arrive at one of two possible conclusions. Either the presentational data will be relatively small and can be loaded all at once, and the front-end map renderer can effectively handle all the required data manipulation, or the required dataset is too big and has to be sliced into tiles, or in other words, smaller chunks of data in order to efficiently handle the visualization.
In the first case, since data can be loaded all at once, all aggregations can be done dynamically, resulting in a more interactive layer, which is usually great. However, size plays a huge role here. As long as the data size remains within a few megabytes limit, most modern browsers should easily handle them. Additionally, the data would have to be prepared in a desired format. A standard GeoJSON file or even a simple object collection could suffice, so that it could be understood by the front-end map renderer library and applied to a chosen layer type, like maybe a points layer, polygon layer, hexagon layer, etc.
Yes, but for the second case scenario, the necessary presentation data is either too large in terms of size, or maybe because it needs to cover the majority of the map, or changes too frequently between zoom levels and different data sets who have to be fetched frequently. In order to manage it properly, the data features should be fed by the front-end renderer only for the currently visible portion of the map that will be bounded by the latitude, longitude, and the zoom level. This preliminary analysis is essential, as it impacts the basic setup of the solution, and changing the system later on could be quite costly.
So how did we start with our project? We took upon ourselves to visualize a custom postal codes layer for the European region, serving as an enhancement layer for a basic map layer. At first, we faced a rather major problem. No mockups. Our only mockup was an actual logistic map hanging on a wall in an office. That, of course, led to several unforeseen problems and increased development time, both of which could have been potentially avoided at the earliest stages of development if a reliable mockup was present.
Yes, also some of the most challenging aspects included the fact that the postal codes layer was supposed to cover most of the map, so a large set of information. We were also supposed to provide a dual use case for our data, so we had to provide one map with a static layer and one map with a dynamic clickable layer. The later one required a reliable user interactivity, which actually came up as a requirement later during the development process. It gave users the ability to click and highlight islands that begin with the same postal code number or letter as the country they belong to. To make that work smoothly, we had to distinguish and save some additional relations between various postal code multi-polygons in the database. Additionally, a preliminary check revealed that the number of postal code polygons, especially those in large cities, is really significant, and it would be too large to fetch them all at once, so we had to use a tile server solution. Our current database used to serve the tile data weighs about 1.5 gigabytes, so only the required data portions are fetched by the front-end map application.
Okay, now let's move on to the next part of the process, which is sourcing the data. Once we have a business and a UX model we are satisfied with and have decided on what needs to be presented, it's time to think where to look for the source data and what type it should be. This step may differ for you if you already have the internal data, such as sales data or client distribution data, so pretty much any data specific to your company. An optional but pretty neat step for this could be enhancing such data with some common geographical units, including countries, administrative districts, postal codes regions, etc. There are multiple sources one can choose from, and all heavily depend on your business case.
Yes, so the data types. There's the company data, the one we just mentioned. It is inside your company data specific to your business company, such as sales, offers, contracts, and logistics data. Essentially any data that your company possesses, but that can be specifically bound to some coordinates or regions. The advantages of the data is that it is free, since it's your company data. The access to it is obviously not a problem. However, it can have a limited scope unless you're working for a corporation and have access to across-industry large data sets. Or maybe you're tasked with just presenting the partial data by your business owners, so you really don't need to seek any other data sources. The other type of data, you have the publicly available data, so some open source data, government data, public websites, statistical data, for example, Eurostat. Such data is also free because of the public aspect of it. It is widely scoped, rather consistent, and more often than not well documented. However, depending on the popularity of the region you are interested in sourcing, it can end up being quite patchy and in need of additional enhancements. Consider, for example, the OpenStreetMaps, probably one of the largest open source geographic demographic databases that is updated and maintained by a community of volunteers. Using it for sourcing data on popular areas like large cities in Europe and the US, it's pretty reliable, but looking for accurate and detailed data for some smaller cities on smaller regions, it could end up being tricky. Additionally, anybody altering the data could provide us with some incorrect information, if temporarily only. Bear in mind also that Some countries might not be formatted properly, and merging data from different countries, completely different data structures, can add some additional development burden. It is also worth noting that some license requirements must be checked, even for open source data, and you have to remember to add the attribution, like credit from the source data in the form of a little label on the map with a link to your open source data.
Another type of data is the commercial data, which usually comes in ready-to-use neat data bundles in common geospatial formats. Such data is coherent, verified, and providers usually keep the data consistently updated. If you know what you are looking for, this is probably the best option to aim for. However, it can end up being a pricey one, but can speed up the development process. As sourcing raw data and maintaining it is quite a complex task on its own, it may be better to leave it outsourced and focus on developing your solution using a ready data bundle. Keep in mind that sometimes you have imposed requirements by your business and need to use specific sources without much room for using any alternatives.
Yes, in our case, we tried a mix of few of those sources. We started with open source data. In fact, we used the OpenStreetMaps, but soon realized that that was not enough because of how unreliable and patchy the data ended up being regarding the postal codes, especially for some less common areas. So we wanted to try combining data from different government sites, but downloading, formatting, and keeping it updated seemed pretty unrealistic with a team of our size. Also finding enough sources for all the countries we needed, as well as translating everything, was simply too much effort in the long run, and the cost of that was too unpredictable. With that many unknowns, we ended up reaching for the last possible option, so commercial data. At the time when we started working on this layer, there was only one reliable source we could find. Currently, there are more commercial sources of geospatial data, usually merged with some additional demographic data. So, depending on the complexity of the data, there usually aren't that many providers you can choose from. But you can often try the thing that we did. So try some open source data, try to combine it, some more sources to achieve a viable, useful application. And if that fails, just try to find some ready-to-use commercial data.
Now, let's talk about the most interesting phase of the process, which is the data preparation step. It consists of three main aspects: data import, data transmutation, and data serving. The whole process should be coded or scripted depending on the complexity. Sometimes a few bash files executing some SQLs should be enough. And sometimes you might need a dedicated updater-like service that will serve as a manager of the whole process. It may enable you to view the build or update progress, which makes it especially neat when its duration is measured in hours or even days. What's essential is that the process has to be repeatable, with very little or preferably none manual intervention.
So in order to begin your work with data processing, some kind of geospatial database is required. Examples of such database include PostGIS or PostgreSQL, Oracle Spatial and Graph, Microsoft SQL Server with spatial extensions, and some others. Such database provides specialized data types, indexing methods, and special functions that for storing and querying geometric and geographic data types. I personally prefer using the pgadmin administrative tool for PostgreSQL because of the very useful ability to view the geospatial data directly on a basic world map. That really helps to grasp a quick context of what the data represents.
Okay, so let's start with the data import step. So you have to have a ready-to-use database and some selected data sources and the data that you need to load into the database. Usually, the source data providers will give you a hint or even a ready script or a simple program for moving the data into the most common database types. Your own company data will probably be stored in some common formats that can easily be moved into geospatial databases with some SQLs. So importing the data is really not that big of a deal.
Yeah, and then comes the fun part, at least for me, where you can dive into the data itself and check its structure to see how it is designed in order to get a better understanding of it. You should look for any anomalies and edge cases, for example, abnormal data structures for different geographic or political regions. Also look at the density of the data. Maybe some regions will be very feature-rich and you would wish to present them in a different way than the more sparsely populated ones. Maybe some parts of the source data is useless for your application and maybe better to just remove it in order to maintain a better readability of the data. Remember that no data is initially perfectly suited for you, so pick what you really need.
Then there are some optional steps available, depending on particular use cases. You can transfer the data into some common data model, enhance it with some additional business information that you possess or merge with other data sources available, essentially creating unique information synergies. Another important issue unique to presenting data as a map layer is the concept of zoom levels. The data has to be aggregated and simplified when viewed from above. For example, when you look at the map of the whole Europe, you wouldn't really like to see all the single data points like street names, because it would just be an incomprehensible mess. More granular and detailed data has to come into picture gradually as the zoom level increases or when the user zooms into a particular region. Just as the detailed data is important, sometimes the aggregated data is visually more compelling and reveals more insight, like a heat map or a hexagon distribution of most common features. For example, the number and frequency of road accidents.
So now we have the source data imported, transmuted and enhanced. We have some samples that look promising for our solution. So the last step will be to prepare the data to be served to a front-end application. Depending on the size of the finished data, it can be either served as one or multiple, but not really many, large files, usually as a GeoJSON format or a widely used format for representing geospatial data, or any other format supported by a front-end mapping library. This will more often be the case if your data consists mostly of point data and not polygon data. Then this will require just a simple backend server responding to standard HTTP requests, or potentially even an Amazon S3 bucket could serve your needs. But if the data size exceeds the threshold of a few megabytes usually, it's more optimal to chunk the data and serve it to the front-end application, the so-called tiles. So small chunks of data fetched from the server, whose location is defined by the latitude, longitude, and the zoom level. Such solution requires some specialized server type that is able to slice the data into required tiles. And there are many open source and commercially available applications like Mapbox Tiling Service, GIS Server, MapTiler, Tegola.io, just to name a few. Commercial ones usually can provide you with a whole stack of tools necessary for bootstrapping the whole layer and the whole application, but open source solutions tend to be just as good. Of course, they require a little more effort to set up. Using a tile server forces you to think of the data in terms of layers that can be separately presented and styled and interacted with. It generally gives you a lot more flexibility and control over the data, but also requires some more specific and technical knowledge.
So how does the data preparation process look like in our case? The source data that we had available was in the ESRI shapefile format. It is widely used format in the geographic information system industry for storing and exchanging geospatial data. That was a mouthful. There is quite a few easy-to-use tools that enable easy transfer of those shapefiles into a Postgres SQL database that we decided to use. So after importing, we took a look at the source data and we identified that most countries had a distinct postal code's length ranging from 4 to 8 symbols. There were also some edge cases. For example, Poland and Portugal had dashes in their postal codes. And the structure of British codes was pretty unique and even more specific, so they couldn't be aggregated as easily as the other codes could be. Also, some shapes of the postal codes we received had very complicated multi-polygons incorporating thousands of little islands, which we eventually had to simplify.
Yes, so all these little things, they had to be accounted for, and the data had to be transmuted into a more common presentable model for all countries. Later on, we tackled the polygon aggregations mechanism, merging the little unitary postal codes into larger regional ones. We also played for some time with choosing the correct labeling algorithm so that the actual postal code value will be presented in the visual center of the polygon, because mathematical center for an oddly shaped postal code could lie outside of its boundaries, and we didn't want the label to be placed outside of the polygon. And finally, we ended up creating just two distinct layers, just one for the polygons and one for the labels, served by a tile server in order to fully leverage the smooth aggregation and simplification mechanisms of such a solution.
When designing a map data layer, there is another crucial issue to bear in mind: the maintenance and data updates. Keeping the data fresh is usually essential to keep the map layer useful over time, as most data will become obsolete. Some applications will have to be updated more frequently, depending on the use case and data depreciation rate. For example, a data for a map with live traffic would have to be updated every minute or so in order to be usable. But on the other hand, a map layer presenting some business size distribution could be updated every week or even a month. Presenting map layer solution with historical data or rarely changing datasets might even not require an automated update process and can only be rebuilt when adding some new features or capabilities.
Yes, but moving on to datasets that do require updates. The easiest solution, which is possible if the dataset is not extremely large or the required update frequency is low, is to just automate and repeat the initial process of data fetching, parsing, and moving to servers. Such approach has many advantages. There is only one single process to maintain, one to process to handle the building and updating. It's the same process. So there will be no bugs with broken update processes, because sometimes it is hard to keep the whole update process as one transaction and then roll back it if something goes wrong. That can potentially produce some really hard to trace inconsistencies in the data. This approach is easier to implement with the file server solution, so generally with smaller data sets, because the amount of time and resources spent on redundant rebuilding work is really negligible. It is harder to do it if you have a tiled server, because generating lower, more detailed zoom levels is very time and resource consuming, as the number of tiles that has to be generated rises exponentially with each lower zoom level. So another approach is to design a separate update process, very similar to the build process, but working only on the partial patch dataset provided from the source and merged at the end with the current dataset version. That, of course, requires additional setup and additional testing of the merged data to make sure that everything during the update went smoothly, but can be necessary in order to keep your map layer useful after the initial deployment.
So how did we tackle the update problem? Well, we didn't really have much choice here. The source data provider does not give us regular update patches. Instead, we receive a whole new dataset once a year. Also, we couldn't fully automate the update process as the changes in the data for specific countries have to be identified and some new edge cases may arise. That would require our attention, of course. Usually the problem lies with more granularity, like more detailed postal codes and an increase in their number. So basically, every year we assess a new data and make some minor or sometimes larger adjustments and just repeat the whole parsing process that in our cases takes roughly about a week.
So now for the last part, let's talk a bit about the visual side of the data that we just created. We'll not delve into the actual UI design process as it is a very large topic, maybe for a separate discussion. We'll talk about where to put the style definition depending on the chosen solution. So if the data is served as single files, the style has to be defined directly in the front-end application. It is best to leverage some ready-to-use visualization libraries like deck.gl or mapbox.gl that are really powerful tools enabling you to create stunning effects with quite limited effort. They are very good with point data, they can handle aggregations very well, and they're optimized to cope with really large data sets. If you go with the tile server solution, the decision becomes a bit more complex, depending on how would you like to render the data. Most backend tile servers have two options. They can serve raster tiles, so essentially just square images rendered server-side that can be cached. With such approach, the data and style definition is completely hidden from the user, and there is no work to be done by the front-end renderer aside from fetching the images and just displaying them correctly. This, however, comes at the cost of absolutely no interactivity options, so the renderer doesn't really know what features are present in the image. So the second option is to serve the data as vector tiles, a type of protocol buffer that map rendering libraries can easily decode. Because styling the data is done by the renderer, it enables full interactivity and even some dynamic changes of the whole style, like changing the colors, enlarging some features, using dynamic translations. Such protobuffer files are also lighter in size than images, and when zooming in this layer, the user experiences a much more smoother feeling when zooming in. But because rendering is done by the client side, there may be some issues with older versions of browsers or even GPU drivers for some older computers, which actually happened in our case.
Then there comes the question where to put the style definition. Generally, they can be kept on the server and fetched by the front-end application. But highly interactive layers may require to dynamically modify the style so it can be also embedded directly into the code itself. So in our case, we first put the style definition on the server to be available to fetch together with tiles. And that was enough for the general purpose for non-interactive layer. Although we encountered the problem that the layer didn't show for some users, about 10% of our clients. And after investigating the problem, it occurred to us that it was a hardware issue. So we implemented an additional check for the application to decide whether it should fetch vector or raster tiles, enabling the solution to work for everyone. Slightly worse performance for the 10% of those users.
Then we also had to check to implement executable layer of postal codes. So we embedded a similar style into another application that fetched only the data from the server, but was able to change the style dynamically and pass the click or hover event effects to other parts of the system. So basically, we ended with one server with some sort of a hybrid solution for two front-end applications. That's all that we have for you today. So just a recap of what's required to implement a custom map layer solution. So first, a good business model, a mock-up or a vision of what's really required. Then defining the data size requirements, seeking and finding the appropriate source data. Then the bread and butter in designing the data parsing process. So importing the source data, parsing and modeling the data, creating a final usable data set, either as a database usable by a tile server or some ready-to-serve files understandable by map rendering library. You also have to consider the data update process, whether it is a full regeneration is possible or you need to do partial updates. And then finally, design the map style and put it in an appropriate place to be used by the front-end library. We didn't really cover the subject of the UI design, as I said earlier, so styling the layers and the front-end application possibilities. This is a very large topic on its own. So let us know if you would like to hear more about that part. But for now, thank you and good luck designing your own solution.